In this video, we're going to derive the concept of surface area of revolution. To start, we're just going to make a sketch of some function f of x. Right, we're going to say that f of x looks something sort of like this. Right, pretty much we're going to say it goes between these 2 points right here. So f of x, we're going to say, looks something like this. So this right here is f of x. Right, so the whole idea of surface area of revolution is if we were to revolve f of x about some axis, we're going to form some surface. The whole idea is what is the surface area of the surface that is formed. So let's just say we were to revolve f of x about the x-axis. Well, in this case, the three-dimensional shape that we get will look something sort of like this. Right, so pretty much it would have something looking sort of like this. So this right here is basically the three-dimensional shape that we would get from revolving f of x about the x-axis. And so basically the idea is, for surface area of revolution, what is the surface area of the surface that we have formed right here? Right, not including the area of these circles, right? The surface area of the surface that we have formed here. Well, how do we do that? Well, what we can do is we're going to integrate the surface areas of frustums. Now, a frustum is basically a shape that looks something sort of like this, okay? Not too complicated, really. It's actually pretty simple. Right? Frustum looks something like this. And basically, the whole idea of a frustum is it's basically a part of a cone, but it doesn't include the pointy part at the top. Or another way you could think about it, you could think of it as a cylinder that's slanted on both sides like that. That's a frustum. And the dimensions of a frustum, very much what we could say is, we could say that this right here and this right here are the two radii of our frustum. Right? The smaller radius, we're going to call lowercase r, the larger radius, capital R. And also this length right here, capital L. Right? These three dimensions define any frustum. Right? And so what we're going to integrate is we're going to integrate these surface areas of really thin frustums across our surface. Right? And we're going to say that our frustum looks something sort of like this. Right? All right, so this is basically what our frustum looks like, and we're going to integrate the surface area of frustums all the way across our surface. And so really, the surface area of our frustum is basically the surface area at this really thin part right here. So pretty much all the way along this frustum, that's where the surface area of our frustum is. And we're going to indicate that as dA, right? So to find the surface area of the surface that we have formed here, what we're really doing is the integral of dA, all right? We're integrating the surface areas of these frustums, all of them along our surface to get the total area of our surface. So next thing we have to do is we have to write what dA is in terms of things we know, like in terms of f of x. So to find dA, it's pretty much the area of the surface area of a frustum. And really, we got to know what the surface area of a frustum is. And it turns out that the surface area of a frustum, right, the surface area of a frustum is going to be pi times r plus r times L. So this is the formula for the surface area of a frustum. And I actually made a video deriving this formula for that. And I'll link in the description below if you have no idea why this is what it is and just kind of feel like this should make sense first. So I'll just link that down below. But really, basically, if we know that this is the surface area of a frustum, then we could use this to find what dA is, because this is, of course, just the surface area of this frustum right here. So really, the surface area of a really, really thin frustum, right? We'll still have pi. But really, what are the radii of this frustum? Well, if we have a frustum that's really, 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 really thin, then these two radii are going to be like literally nearly the same exact value if we have a really, really thin frustum. So really, these two radii are going to be exactly the same effectively. And so we could just say that the radii are the same. So we're just going to say that both of these are the same exact thing. So we're going to say it's r plus r. It's the same radius. And L is really the length right here. And when we have a really, really thin frustum, L becomes really, really, really small. In fact, it's a differential length, right? We're going to call it DL. And so really what this is, it's DL, right? And so really what dA is, it's 2 pi r DL. So this is what we're going to substitute for dA back into our integral. So what we get is A is just the integral of 2 pi r DL, right? So this right here is actually the whole idea of surface area of revolution, right? If you know the radius of what you're integrating, if you know the radius of your really thin frustum, and basically it's integrated along DL. So basically the radius, R, would be represented as the radius right here. It's basically the radius like that. And then DL is, of course, that really, really small length of that right there. And what DL actually represents is the arc length of f of x, because it's going along the curve of f of x. And so that's the whole idea. And so this works for basically a function it's pretty much, you know, a function that's revolved about any axis. This is the idea for surface area of revolution. But in this case, we're revolving f of x about the x-axis. Pretty much, we're able to say that our radius right here, goes from the x-axis to the function f of x. So really, this radius right here is just the y value of our function. It's just f of x. And dl is, of course, the arc length of f of x, which we know what arc length is. It's just going to be this, right? We know what arc length is, right? We remember from arc length that this is all it is, right? So it's this thing right here. And so this is really the whole idea of surface area of revolution. And we could just pull out our constant 2 pi to the front of the integral. And so next, of course, since we're integrating with dx, we're going to say that this goes from, a value right here, goes from a to a value right here, b, right? Because that would go from this point to this point. So going from a to b, pretty much that would be our bounds of integration, going from a to b. And so this right here is the whole idea of surface area of revolution, in the case that we're revolving f of x about the x-axis, which in most cases it is. Otherwise, you're probably going to be revolving about the y-axis, and so it looks pretty similar to this. And this right here is the whole idea of surface area of revolution for a function that's revolved about any axis, right? And that is pretty much the whole idea.